So I'm going to be talking about two sorts of virtuous triangles. So one is the triangle which I think is formed by parahydrogen long-lived states and hyperpolarization, and I think we've already heard quite a few things in that line already, and I'll be going into what I mean by that in a minute or so. There's another sort of triangle which I've just become quite interested in, so I'll explain later what that means. But first of all, the first triangle. So already today we've had a great deal of detail on this. So there's no explanation needed in this meeting about what parahydrogen is and how it's made. That's already been well covered today. Enriching hydrogen gas in the paraspin isomer, which is the nuclear singlet state. Hyperpolarization, we've also heard much about already. It's a bit hard to define that in a sort of uncontroversial way, but I think we all know what it means roughly, which is that you have much more spin order than you have in an ordinary NMR experiment, in which you start by equilibrating the sample thermally in a strong magnetic field. And there are various techniques for producing such hyperpolarized states. DNP, as Jan Henrik told us about his tremendous developments in that area. Other techniques, such as optical pumping. The less well-known one, which we've also worked in a bit, is quantum rotor-induced polarization, which is a phenomenon which happens in particular for some methyl groups. Then we have long-lived states, which again may be defined rather, sometimes not so easy to define exactly what these are, but generally speaking, they're configurations of nuclear spins which last much longer than the nuclear T1. And a very important example, we've already heard a lot about it, is what's called singlet order, which is a population difference between the singlet state and the three triplet states in pairs of spins half. And there are various techniques for generating such states, starting from thermal equilibrium magnetization in ordinary NMR experiments. And we've already heard about some of those techniques, M2S and the slick method. And these phenomena, they form a sort of triangle. One can actually go in many different directions between them. The one which is of most interest in this meeting is that one can go from parahydrogen to a long-lived state on the product molecule in either a hydrogenative experiment or a Saber experiment, and thereby access hyperpolarized nuclear singlet order, which can be converted into states which give strongly enhanced NMR signals. And I guess more or less that's what this meeting is about. So if we just want to define the terms, if we talk about pairs of spins a half, which are either magnetically equivalent, as they are in hydrogen itself, or have a small degree of magnetic inequivalence, which is often the case in the spin systems we're interested in this field, then the spin states can be classified as the nuclear singlet state, which has nuclear spin 0, so does not give an NMR signal, and the three components of the triplet state, which has nuclear spin 1 and does give an NMR signal. And in a density operator description of the system, an operator of the form IZ represents the difference in populations between the upper and lower components of the triplet state. So more population in the lower triplet state than the upper triplet state. That gives rise to nuclear magnetization, which can be observed in a high field NMR spectrometer through the usual pulse FT methods, or also in an ultra low field magnetometer as well. But then we also have a different type of order, which is called here singlet order, which is population difference between the singlet state, which is overpopulated in this case, and the triplet state, where the three components are equally populated. And in the density operator, that's represented by an operator of this type. And we can see from its form that it's scalar, it's isotropic, it's invariant to rotations. And in addition, because the transitions between the singlet and the triplet state are symmetry forbidden in many cases, that type of spin order often has a very long persistence time, which may exceed the ordinary T1 by many factors. So for many years now, we've been conducting in the group different types of singlet NMR experiments. The typical plan for such experiments starts by allowing the sample to reach thermal equilibrium in a strong magnetic field. That corresponds to a term IZ as the spin operator. We have some manipulation which generates from that initial state the singlet order. That may be allowed to rest or evolve for some time interval, which may then be varied in a series of experiments and reconverted back to magnetization for observation. And now there's a whole sort of botany of different methods for doing this conversion from thermal equilibrium to singlet order. The first experiment of this kind was actually done using a field cycling method in which the sample was removed from the magnet. But there are numerous methods using hard pulses in strong fields. There's the M2S sequence, which our group developed maybe about 10 years ago now. There's actually now two generalized versions of that, which have a somewhat broader range of application with very similar names, actually. There's GM2S, which is from our group, and GCM2S, which is from Stefan Glogler's group. There's methods which use very weak selective radiofrequency fields, such as the SLIC method, which Stephen de Viance told us about very beautifully. Very beautiful set of methods. And then various methods involving sweeps, which can be in ultra-low field in some cases, or in intermediate fields. So all of these different methods have advantages and disadvantages in different domains of use. And they all intersect to some extent with the sort of methods which are used in FIP experiments. The M2S method actually involves a set of spin echo trains involving pi pulses, where the timing is matched actually to a coupling in the system for a single pair of slightly inequivalent spin to half. Then the frequency of this repetition matches the J coupling between the spins. And then there's a couple of 90-degree pulses involved as well, and one strange extra delay, which turns out to be necessary in the spin dynamics. Simulations can be done which show how the magnetization of the system is passed through various other terms in the density operator, eventually to singlet order. And as I said, this method was developed some time ago. It's very similar to the SLIC method. The SLIC method is much simpler, just involving a single radio frequency pulse, so that's very convenient. But the M2S method and its variants do have some advantages in that they're actually very robust to field inhomogenators and so on. One example of the use of these methods, a demonstration some years ago now on this particular molecule here, which contains a pair of carbon 13s, which was designed in order to test how long lived a singlet state we can produce. And in this case, we succeeded in solution of getting a singlet state with a lifetime over 1 hour. And I believe that Pepe Pelayo, who maybe I think is speaking later in the meeting, will have a bit more to say about that. Right, so that's the virtuous triangle then. Generating parahydrogen, using that to populate long-lived state, a form of hyperpolarized spin order, and then to generate enhanced NMR signals. And our group has not been that active in this area. But we've essentially nibbling away at a few of the sort of little corners of the area, which just trying to find something a bit different to do. One of them is to exploit some chemistry which is a little unconventional. Most of the hydrogenative experiments end up with the hydrogens on both sides of a double bond. So that would be called cis-vicinal hydrogenation. But in some circumstances, you can get actually transvicinal hydrogenation, in which the two hydrogens end up on the opposite sides of a double bond. And one important molecule of that kind is fumarate. Barbara Rybka and James Eales, who was then in my group, performed some work together, which we published a few years ago. And I think James is going to give a talk, or in the program, if the program is to be believed, he's going to give 2 talks. I don't know how he managed that, but anyway, we'll hear from James later, I think. We've also been doing some work with geminal Fib, in which the 2 hydrogens end up on the same carbon atom and so generate a methylene group. And Lorinas is going to talk later today about that. That's potentially interesting because a lot of molecules, of course, have methylene groups. And also the 2 protons are close together, so that gives a very long-lived singlet state, typically. And in addition, we've been collaborating with a group of Marcel Utz, who will be also talking later today on the work of doing parahydrogen on a chip, so FIP on a chip, which is showing some promise as well. So now I would like to switch to essentially the second triangle I'd like to discuss, which is this one here. So let me explain what this triangle is about. So this is gets a little bit theoretical, but not too bad, I hope. So we describe the state of an ensemble of spins by an object called the density operator, and technically it's given by this Kepler product averaged over the ensemble. And in NMR theory, we expand that density operator in terms of a set of operators. So we have the unity operator, which is always there, divided by the number of states of the system. So if the density operator was just given by that unity operator, then it would mean that all the states are uniformly populated. And actually that would be a state of maximum entropy. So minimum spin order, and actually no useful information can be derived from it. So the interesting terms are these extra terms here, which are other operators multiplied by numbers. And loosely speaking, we can call the numbers polarizations, and the operators are different modes of spin order. So technically they're orthogonal and they're traceless. The question which I want to ask now is a very basic one, really, and which is basically what numbers A, B, C, and so on are actually possible physically. So we're not talking here about what can you actually attain in a given experiment. We're talking here about what can you attain in any possible experiment or in any possible preparation of the system. And surprisingly, as far as I know, and I may well be wrong about this, but this question, the bounds on the physical bounds of possible spin states, has rarely been asked. In fact, I'm not actually aware of at least an NMR paper asking this question. In a way, it should be the first question you would ask in NMR theory. Before even discussing what an experiment gives, you would probably first of all like to know what could you possibly have. So the rest of the talk really is about that question. So let's just take a simple example. Yeah, okay, so the basic idea is that you have, if you drew these, there's many different numbers here, but if you just took two of them, A, B, you can make a sort of two-dimensional space. In fact, it will have many more dimensions because of the number of operators here. And there will be some sort of area within that space within which all physically possible states have to be located. So anything outside of that boundary would be non-physical and would be physically invalid. It could never be attained by any preparation of the system. So we know this very well actually for single spins a half. So if we just have isolated spins a half, the three operators we're talking about could be called the polarizations along the X, Y, and Z or Z axes. So the number Px then multiplies the operator Ix, which in this case is the polarization operator for along the X-axis. And I think we know very well how this works out for single spins a half. That the sum of the squares of the three polarizations has to be less than 1. But beyond that, there's actually no other constraints. So you have, in 3 dimensions, a spherical bound of radius 1 on the polarization of the system. And that's very trivial, really, and is embedded in the way we think about NMR. So much so that it's hard to imagine that it could be any other way. And we all know pictures of magnetization vectors, which are essentially moving around, which represent points moving around in this space. And we also know that you can never go beyond this space. So you could never create a polarization larger than 1 in any particular direction. So the physical meaning of these states are as follows. So for example, complete polarization along the Z-axis, which is the aim of hyperpolarization experiments, corresponds to pulling all the populations down to the alpha state, the lowest energy state. And that can indeed be achieved to some approximation by hyperpolarization methods. While a state with magnetization vector of length 0 just represents an infinite temperature state with equal populations along the 2 axes of the 2 states, excuse me. Right, so that's what happens for single spins a half. So that sphere essentially describes all the possible states which the ensemble of spins a half can have. So now let's suppose we get one more complicated. We have pairs of spins a half. And of course, this is the situation which very often comes up in FIP experiments, amongst others. Now, if you have 2 spins a half, you have 4 energy levels or 4 energy eigenstates. And that means you have 16 possible operators. One of them is the unity operator, which is now divided by 4 because there are 4 states. So in fact, you have a space of 15 dimensions in which you have to represent, in which you can represent the state of the spin ensemble. So it could be represented as a vector in 15-dimensional space. But of course, we can only look at some of the dimensions at once, at least if we want to represent things graphically. So we have 3 operators which are X, Y, Z, the polarizations, the polarization operators. For technical reasons, these are actually a half of the angular momentum operators in this case, but let's not worry about that. But again, for this three-dimensional subspace, we have the same intrinsic bounds. So the three polarizations added together vectorially have to be less or equal to 1. So you can never have more than polarization of more than 1 in any direction. So at least in 3 of these 15 dimensions, then you have spherical bounds. But we have many other operators. And 2 of the interesting ones are the singlet order, which can be represented by an operator of this kind for the scalar order. Physically, that represents population difference between the singlet state and the triplet states. And its maximum possible value is 1. And we also have another possible order as well, which I've called here P20. So we can call that the rank 2 order, or equivalently the dipolar order. In solid state NMR, that would be called the dipolar order. And it's proportional to a rank 2 spherical tensor operator of this kind here. And the maximum possible order you can have is also 1. So we might well think that the bounds of these 5 operators would also be spherical, maybe in a 5-dimensional space, but still spherical. But that's not true. So in fact, the bounds are triangular in 2 of the 15 dimensions. So if we plot the Zeeman polarization operator against the singlet order operator, then the region of physically possible states is actually bounded by this triangle here. So somehow we have to imagine that we have a 15-dimensional space, which if we somehow manage to distill out 3 of the dimensions, we get a sphere. But if we distill out 2 dimensions, we get a triangle. And the physical interpretation of these points on the triangle are pretty straightforward. So maximum singlet order has everything in the singlet state. Maximum Z order has everything in the lowest spin state. And that means, it implies immediately that the singlet state must be depleted relative to the triplet states, which is why you can't have a point of polarizations, 1 along the z-axis, without also having -1/3 of singlet order. And the same goes for the state with negative Zeeman polarization. It must also have -1/3 of the singlet order. And then what about the rank 2 order? That comes in as well. And actually, if you take that into account, you find that the bounds on that are actually form this rather strange polyhedron in 3 of the 15 dimensions. So what's plotted here is vertically is the Zeeman order. So maximum polarization at the top and negative polarization at the bottom. Singlet order going left to right in this aspect. And the third axis is the rank 2 order, or here dipolar order. So the physically possible states are bounded, in fact, by this strange polyhedron in 3 of the 15 dimensions, so not a sphere at all. So now let's look briefly at how the point, so a point in the space represents a spin state, essentially. And now those points move according to the spin dynamics. So the equation of motion is called the master equation. And the one which is most commonly used in NMR theory is called the inhomogeneous master equation. And it comes from the 1950s and 1960s by these luminaries of the field, Bloch, Abraham, and Redfield, and probably several others contributed as well. But the aspect I'd just like to emphasize here is something which I found very surprising when I was first exposed to this a year or so ago. is that this equation actually only works when you're very close to the origin of the space. And actually that's something that these guys knew very well. But I think in NMR, since those days, we've tended to forget it. At least.
Sorry for interrupting, but you're already in the Q&A time, so try to wrap up.
Okay. Okay, I'll then wrap up very quickly. I was going to try to explain quickly how one can show from these diagrams that the ordinary master equation leads to a conflict with the physical bounds on the system, but that my student Christian Benks has developed a different master equation, which is based on Lindbladian techniques, which should be used or may be used to describe the relaxation of these non-equilibrium systems of the type involved in FIP. Of course, FIP involves spin systems which are very far from equilibrium. So to model the behavior of those systems, sometimes one may need to solve the equation of motion for the spin ensemble. And the ordinary master equation, which is used for that purpose, does not do the job. It actually conflicts with the physical bounds of the spin system. But this new type of formalism, or let's say a reworking of an old formalism, because this is very well known to people in open quantum theory, but adapted for NMR purposes, is one of the better ways of doing that. So I'd just like to publicize that piece of work. And finally, I'd just like to thank very much the members of the group who've contributed to our parahydrogen work. Christian, you'll be hearing later, I believe, from James, Eels, these other people I will mention as well, Barbara, who originated the fumarate work, and Lorinas, I think you will also hear from later in the meeting, and these groups who we enjoy a very nice collaboration with. So thank you, and I'll be very happy to answer questions.
Yeah, thank you so much for this exciting talk. I must admit myself, I never thought about these physical boundaries in these higher order situations, and I bet many other people haven't. Sadly, we don't have time for many questions, so I will just ask the first one that was given to me, which is towards one of your earlier slides. Doesn't a vector with zero length violate the uncertainty principle?
Oh, wow. I don't think so, because one's talking about here about density operator, the representation of the state of the spin ensemble in Liouville space. That's different from a vector representing the state of a single quantum system in Hilbert space. But I think that's probably something we need to discuss offline. I believe there's some type of device where we can talk about that together somehow. I'm not quite sure how to do that. But, so I can't answer the question in brief, but we can talk about it.
Okay, one last question, because I think it's so interesting. What are the consequences of using the different master equation? Do new physical predictions arise?
In principle, yes. In our paper on this, actually, then we showed that in a common situation, that one gets radically different physical predictions than the old-fashioned master equation. The old-fashioned master equation, or the inhomogeneous master equation, gives actually very clearly completely ludicrous physical results. In fact, if, well, the situation in that, just to say something briefly about that. So suppose you have hydrogen in solution, and you have pure parahydrogen. So since it's pure parahydrogen, there's no NMR signal. There's no nuclear magnetization. Everything is in the singlet state. But you have a T1 for the hydrogen, And you also have a slow process which converts the parahydrogen to orthohydrogen. And then you ask the question, how fast does the magnetization build up? Well, the correct answer, which is obvious, I think, is that the para to ortho conversion is the rate determining step. So the magnetization builds up very slowly as the para converts to ortho, and then the ortho magnetizes. So the magnetization builds up with the ortho to para conversion rate. But incredibly, the ordinary master equation, the inhomogeneous master equation, which has been around for 50 years at least, predicts that it builds up with T1, yes, which is clearly completely ridiculous. While in this case, the Lindblad master equation predicts the correct result. So, there are in some cases very large discrepancies between these two equations.
Yeah. Thank you so much. And sorry for everyone else, you will have to ask all those questions in Slack now. And yeah, let's please thank the speaker again, virtually, or however we can do this.